In this next chapter, this next unit, we'll be dealing with series, but we kind of introduce series by introducing the concept of sequences. And today we'll kind of look at some of the, maybe some of the terminology, some of the procedures that may not have been covered on the online material, but it's the same ideas, maybe some different terms. So kind of clear up some of those items as we relate it to the worksheet I gave you. Now, one thing that I don't think he mentions is the word recursive. And this is a very important term when we talk about sequences, and especially the notation. Now, when he discusses Fibonacci sequence, that is actually a recursive sequence, but it's kind of a more complex recursive sequence than what we usually talk about. And just to give you an idea of the notation and things with recursive sequence, refer to number 8 on the handout. Now, number 8 is not one of the problems you'll be working on, but 7 is. But number 8 says a sub 1 equals 6, and then a sub k plus 1 equals 1/3 a sub k squared. Now, it says, right, the first 5 terms of the recursively defined sequence. I may not go 5 completely, but give you 2 or 3 maybe anyway. Well, this is our starting point. In a recursive sequence, we have to have something to start with, because then the next one, let's say if k is 1, then we would be saying a sub 2 will equal 1/3 of a sub 1 squared. And this k plus 1 is what we consider the next term using the previous term. Okay, so a sub 2, 1/3 times 6 squared, well, 36 times 1/3 would be what? Oh, such big numbers for a Monday, especially Monday after spring break. Be what, 12? Okay, I can at least do that. I'm still alive. So then a sub 3 would be 1/3 times a sub 2 squared. And of course, 12 squared, 144 times 1/3. I'll let you grab your calculator and do that, whatever that may be. But that's what we mean by recursive sequence. The next term uses the previous term to calculate it. Okay. We don't see a lot of that, but it shows up once in a while in different things. And like I said, the most famous sequence that most famous in the mathematical world, most people probably have never heard of it before, but Fibonacci sequence, again, is a recursive sequence. Okay, next little topic. In dealing with sequences, and especially series in the next few sections, we're going to be dealing with a notation, at least in some problems, of factorial. Some of you have dealt with factorial before, some of you have never seen it before. And so what we're going to look at first is the meaning of it. And this little exclamation point, well, in mathematics that means the factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. It's all of the natural numbers multiplied from that number down. Or you could say 1 times 2 times 3 times 4 times 5. The order doesn't matter because it's multiplying. So when we say n factorial, well, in that case we usually start with 1 and go up. We just kind of have to say, okay, 1 times 2 times 3 and so on. And then just to give you kind of an idea what the last 2 or 3 numbers would be, we could represent n factorial this way. And in series, we're going to see n factorial and different combinations of n factorial as we move into some of the more complicated stuff. Not right away, but we'll see this in some of the series we deal with. But some of the problems that we'll run into will be simplifying factorial expressions. So let's look at number 20. We'll jump into one of the most complicated factorial expressions you'll see. Now notice this is the quantity of 2n plus 2 factorial and the quantity of 2n factorial. It's not 2 times n factorial, but 2n is the quantity we're factorialing, or however you might say that. Well, let's look first at the denominator and see what that means. Of course, we'll 1 times 2 times 3. What would the term before this one be represented as? The second to the last term of 2n factorial would be what? Okay, would be the second to the last one, and then finally the last one would be 2n. Now the one before this one would be 2n minus 2, then 2n minus 1, and then 2n, the factors there. Well, let's take a look at the numerator then. And this one gets even more interesting. We'll back up. We'll start with this one, and then the next one, and then the next one. Well, what more do we need in the numerator that we haven't put yet? Okay, 2n plus 1 and 2n plus 2. And as you can see with the fractions, well, all of these will cancel. 2n minus 2, 2n minus 1, 2n, I guess, 2n. So in the denominator, well, technically we have 1 left in the denominator, but we have 2n plus 1 times 2n plus 2 left in the numerator. So all of that would simplify to this right here. So in this unit, we're going to see some factorial representations And again, some of you may have dealt with factorial before, this may be the first time you're seeing it. It'll take a little getting used to, but the concept isn't so bad once you kind of understand it's just the natural numbers increasing by 1 each time with the factors. Okay, that'll kind of introduce you to that notation. And then there's one further kind of verification of what they're talking about in the worksheet. On the second page of your worksheet, number 61 and 63, the worksheet says use theorem 9.5. Well, in the online material, this is the theorem, the statement about monotonic and bounded sequences. And we can basically state it: if a sequence is bounded and monotonic. Monotonic means continually increasing or continually decreasing. Then the sequence converges. Now, the online materials would say the sequence has a limit. Well, the limit exists, it would converge to that value. So, kind of, again, same concepts, but a little different terminology that we use here. Okay? So that pretty much kind of explains some of the slight differences in terminology. Again, the very same concepts we're talking about, just a little different terms, and hopefully that will clear up some confusion you may have with the online material and the handout. So, time to get to work.